We develop a method named Factored-NeuS, which recovers the surface, materials, and illumination of a scene from its posed multi-view images. In contrast to prior work, it does not require any additional data and can handle glossy objects or bright lighting. Surfaces with glossy materials typically result in highlights. Neural radiance fields model the inconsistent colors as bumpy surfaces. To better handle glossy surfaces, we jointly use surface and volume rendering. Volume rendering does not decompose the reflected radiance, while surface rendering considers the diffuse and specular radiance separately. Moreover, a glossy surface can influence the decomposition of the reflected radiance into a diffuse component and a specular component. Generally, the specular component seeps into the diffuse component, leading to inaccurate modeling as depicted in the figure. To better recover diffuse and specular components, we estimate the ratio of incoming light reflected in a specular manner. Our framework has 3 training stages to gradually decompose the shape, materials, and illumination. In the first stage, the SDF network is trained. It outputs a feature vector, an SDF value, and a normal. The diffuse and specular surface color networks MD, EMS, produce their respective colors CD, CS via surface rendering. These are then combined through a tone mapping to obtain the final surface color. The network MIC produces color C of the sampled points, used for estimating the volume color through volume rendering. In the training process, the overall training loss is defined by 3 loss functions, namely volume radiance loss, surface radiance loss, and regularization loss. These qualitative results demonstrate the effectiveness of the joint optimization of volumetric rendering and surface rendering. In the second stage, we focus on predicting the lighting visibility and indirect illumination of a surface point X under different incoming light direction. Using the SDF in the first stage, we propose to use an integral representation, with the continuous weight function for the SDF to express light visibility. Specifically, we establish a neural network, which maps the surface point and incoming light direction to visibility, and the ground truth value of light visibility is obtained by integrating the weights of the SDF of sampling points along the incoming light direction. Indirect illumination refers to the light that is reflected or emitted from surfaces. We parameterize indirect illumination via spherical Gaussians. We train an indirect light network that maps the surface point to the parameters of indirect light. The ground truth indirect radiance is queried from proposed color network. In the third stage, we use the Ward BRDF model and represent BRDF via spherical Gaussians. The radiance of surface point and outgoing viewing direction can be decomposed into 2 parts, diffuse and specular radiance. To reconstruct a more accurate specular reflection effect, we use an additional neural network MS to predict the specular albedo. The modified BRDF is as follows. For indirect illumination, the radiance is extracted directly from another surface and does not consider light visibility. Our final synthesized appearance is C-pre and supervised via the L1 or GB loss. These are qualitative and quantitative results in terms of chamfer distance on the scenes with high specularities on DTU and SK3D. Red and orange indicate the best and second best algorithms. We further show qualitative results for surface reconstruction compared with many other works on the Shiny dataset, which is a synthetic dataset with glossy surfaces. Our method achieves state-of-the-art surface reconstruction results on glossy scenes. We evaluate the quantitative results in terms of PSN or metric for material and illumination reconstruction on the INDISC dataset, compared with FISC, NDIFRIC, and INDISC. For completeness, we also compare to the case where the specular albedo improvement was not used in Stage 3. It demonstrates the material decomposition effectiveness of our method on shiny datasets with glossy surfaces. Additionally, we visualize some other components, the light visibility, indirect light, and relighting. Thank you for watching. You can get more results and code by scanning the QR code.